lectures. I think there others will join us in the course of the lecture. We'll go on now with our classification problem with the logistic regression and then move to nominal data, ordinal data, and count data. Probably in the nominal one we just discuss shortly and then spend more time on ordinal and count. So what we have done yesterday, we said, well, let us try to model the dependent variable, which is a binary one. So y takes two values, 0 and 1. And we try to model this kind of dependent variable as a function of some features x, for example. First, we discussed why it is not really reasonable to do it using a classical linear regression, because there are a lot of disadvantages which are both from the point of view of interpretation and from the point of view of statistical properties of the model. Then we said, well, let us say that we have some kind of pseudo or latent unobservable variable y star, which actually measures our solvency or insolvency of the client, which is, however, a continuous variable and takes any values from -infinity to +infinity. If we have, or if you would have this kind of variable, then we can apply the classical regression with all the features and some random variable u or residual u. Then we have to build a link between our latent variable and our binary variable yi, and we said, let this be our decision rule. So it is equal to 1, so the client is insolvent if this kind of unobservable variable is positive, and it is the client is solvent if their unobservable variable is negative. Then, very simple trick, we just try to play with all these probabilities here, and we ended up with the following idea that the probability of being insolvent is in fact equal to the distribution function of our residuals. Sorry. The probability of being insolvent is equal to the distribution function of our residuals evaluated at their link function x prime beta. So we can in fact take any distribution function for residuals f, and two most popular approaches are the distribution function of the standard normal distribution, then we'll end up with the probit model, and the distribution function of the logistic regression, which has a lot of different mathematical advantages. Then we'll end up with the logistic regression and the logit model. So at the very end, we have this kind of a very simple model. The probability is equal to this stuff here, and D is some linear combination of our features. The simplicity of that is, first, we have very nice mathematical function exponent, so it is continuous, smooth, so you can do, in fact, whatever you want with that. And then this function here, this ratio here, takes values between 0 and 1. So it is monotonously increasing from 0 and 1. So we get at the end a very reasonable and feasible value for the probability. We can replace this function by our cumulative distribution function for the normal distribution, and we'll end up with the probit model, but this function is not given explicitly, so it's just numerical representation or integral representation for this guy here, so it is not so easy to work with that. Then we talked about their interpretation of the parameters. The only thing what we can learn from their parameters is their impact on their probability. So if parameter is positive, then the probability of being insolvent increases. If the parameter is negative, then the probability of being insolvent decreases. There is something like odds. We've said a few words over here. How can we learn something from the odds? But so some people just look at the sign, some people look at the odds, so it depends on the setting. So then we talked about estimation, it is maximum likelihood, and then we finally came to their evaluation of the performance of the model. And we said that their predicted values or their probabilities lie on this logistic curve here. The red dots are the forecasts, and the blue dots down there are the true values. Those are the good guys. They have the y value equal to 0, so they are solvent, and those are the bad guys. Their value for y is equal to 1, so they are insolvent. And then we tried to develop some kind of performance measures. So we have spoken about their different pseudo R-squares. There are zillions of them. So we looked at 3 of them over here, and the list here contains like 10 others. They all can be interpreted as R-squares. If they're close to 0, they are bad. The model is bad. If they're close to 1, the model is good. So in fact, we don't really have a very good model because all those R-squares are roughly between 20 and 25%, sometimes to 30. So then we said, well, let us try to learn a little bit more out of that. And we built that so-called classification table, or the confusion matrix. This contains, in fact, all correct decisions and wrong decisions which we have in our model. And the only thing what we have to do, we simply have to draw a vertical line over here, draw a horizontal line and there 0.5 over there, and count the observations which are falling in this interval, that interval, and this interval. So in fact, we have correct decisions over there and over there. Good guys forecasted as good guys, bad guys forecasted as bad guys, and then 2 erroneous decisions. Those are bad guys predicted as good guys, and those are good guys predicted as bad guys. All those numbers, n00, n11, n01, and 10, are put into their confusion matrix over there, and there's a lot of analysis what you can do, in fact, with this kind of the table. So let us have a look what happens if we apply, or if we compute that confusion matrix to our data. We set our threshold for the probability to 0.5. So this line is exactly at 0.5. Every single person with a probability of being insolvent more than 50% is actually classified as insolvent, and every single person with probability of less than 15% is classified as solvent. So our confusion matrix looks then this way. There are 479 people which are in fact solvent and are classified as solvent. There are 72 clients which are in fact insolvent and classified as insolvent. And those two guys are, or like those two cases here, they show their erroneous decisions. This is actually the worst one. Those are the bad guys which are classified as good guys. So this is really painful for the bank. So those are the guys who get money but cannot pay back. Let's take their note here. So those guys are in fact bad guys, so the true value of y is equal to 1, but those are classified as good guys. So this is really painful to the bank because those guys get the money from the bank but cannot pay it back. Those guys are also kind of bad decisions of the bank, but those are less painful because those are the good guys who are classified as bad guys, so they simply do not get the money, and the only thing what the bank loses are their interest rates and their like good clients. Those are their guys. The bank loses interest and good clients. So from statistical point of view, those two erroneous decisions, they are both equally bad. This is a wrong decision and this is a wrong decision. From the point of view of the bank, those two decisions are different. So here the bank loses really a lot of money because the bank loses the whole sum of the credit because their bad client is classified as good. And here the bank loses just the interest rate and the good client and the person. So this is a less bad, so this erroneous decision has a less bad consequence for the bank than this erroneous decision. From statistical point of view, we don't care, but from the point of view of the bank, those are like differently bad decisions for the bank. Now let us have a look at the total fraction of correctly predicted persons. So this is their correctly predicted person, this is correctly predicted person, and we have altogether this number divided on the total number of the clients. So in roughly 79% of the cases, their logistic regression made a correct prediction. So these are number here actually tells us, it's like our squirt in how many percent of the cases our logistic regression made a correct decision. Doesn't matter if we talk about good clients or we talk about bad clients. So this number here looks to be large. 78, 79% of so it looks nice. But when we think about the fraction of the solvent clients in the sample, we have roughly 74% of solvent clients. So the whole sample is slightly unbalanced. There are 3/4 or 3/4 of good clients and 1/4 are bad clients. Now let us just thinking about this sentence here. Imagine the following situation. We do the following. Imagine you work at the bank, someone comes to you, and if you want to decide if the person is good or bad, you just toss 2 coins. So a person comes, or client comes, toss 2 coins. If you toss 2 coins, there are 4 possibilities. Either you have twice head, or you have head, tail, or you have tail, head, or you have tail, tail. And you have very simple decision as a bank clerk. You say, well, if I have 3 cases, or 1 case of the first 3, then I'll classify the person as a good client. And if I have 2 tails, I'll classify this person as a bad client. So just toss 2 coins and classify this guy as the good one if you have either head or head tail or tail head, and classify the guy as a bad client if you toss 2 tails. In fact, this procedure, where you don't really look at their questionnaire at any characteristics of the client, will give you the number of correct decisions of 75% roughly. Why? Because the fraction of their good clients is roughly 75%, and you will end up here with good clients also in 75% of the cases. So this procedure here will have their rate of correct decisions roughly of 75%, without looking at the age, debt to income ratio, at any features. Cases. So they don't have to estimate anything. They just rely on this unbalanced sample and just toss coins to predict their quality of the client. In the light of this idea, this result over here, what we got with our logistic regression, is not so good, because we estimated with some heavy maximum likelihood some parameters, we made some predictions and so on and so forth, and we improved the performance of simple tossing 2 coins just by roughly 4%. So this improvement due to logistic regression and due to all this modeling doesn't sound to be so cool if we look at their simple tossing of 2 coins and the unbalancedness of the sample. Now, what can we adjust in our logistic regression to improve the performance? So we believe that the logistic regression in the model we want to use, the only thing what we can calibrate here is in fact this threshold here. Because we picked up here 50% just intuitively. It's very natural benchmark or very natural threshold. If probability is higher than 50%, then it is more probable to have an insolvent client. If less, then it is less probable. But in fact, we can try to change this threshold here to improve our model performance and to improve this number of correct decisions in total. So the idea is, can we change our 50% of